Hello, good morning. I'm Suren Byna from Lawrence Berkeley National Lab. I am a staff scientist and also lead the USA's Exascale computing project's XIO project, which includes software development of HDF5. Thank you, Michael and Kira, for inviting me to give this keynote to talk about parallel I/O at Exascale. And the softwares I would be talking about are HDF5, which is a mature software that has been there for more than 25 years, and also a new data management system called Proactive Data Containers. Okay. Moving on, I move myself here. So the teams that contributed to this slide, these slides, are from multiple teams: the XHDF5 XIO team, EOD HDF5 team, and Proactive Data Containers team. And I would like to acknowledge all of them here. So we all know that scientific data plays a critical role in discoveries, and it is massive. So if we take a look at where the data is coming from, it is coming from large-scale simulations that run on supercomputers and large-scale experiments where a set of inputs are given and outputs are measured, and observational data such as just observing the universe, Earth, earthquakes, and all those things. So if we take a look at typical life cycle of the scientific data, once the data is generated, it is analyzed while the data is where the data is just produced, and it is processed further, or either based on the in-situ analysis or an existing processing steps. And the data is stored, analyzed, preserved, and shared with groups of people or publicly. And when the experiment is or the simulation or observation is refined, you generate data, more data. So this is just one typical life cycle of data, but it is not the only way, and not all the steps may be in the same data life cycle. Okay. So supercomputing systems play a significant role in supporting the data lifecycle. Some of these are where we currently work with, such as the Summit at Oak Ridge National Laboratory, Theta at Argonne National Laboratory, and Corey at Lawrence Berkeley National Laboratory, where I work at. So the components that support data management on these systems are representing the data, such as metadata, data structures, and how the data is laid out in the system, or the data models for that. And the storage includes storing and retrieving the data and metadata to and from the file systems very fast. Data access, not only the data access, but also information access, just the information that scientists are looking for. Facilitating analysis, so once the data is stored on the systems, analysis tools are needed, visualization tools are needed. And when the data needs to be shared or moved to a different system, or the supercomputing system to a local laptop or something, so data transfers play a significant role. So I will be focusing mainly on the data storage and data access components of this system. More specifically, I would be talking about the storing and retrieving of parallel I/O and HDF5. Then what is the software stack, and what are the new features that we are developing in HDF5 for Exascale systems, and also touch upon very briefly on the object-centric data management system called Proactive Data Containers that we are developing. So if we take a quick look at the trends of storage system over the past decades, for a long time, conventional storage system had typically these three layers, memory and a parallel file system and the archival system, where you store the data for a very long term. But the speeds of memory and parallel file system are very different. Typically, the parallel file system is built with hardware devices, the hard disks. The speed gap between memory and storage has been significantly high. So to reduce that gap, in the past decade, some of the systems have been adding burst buffers. For example, on the Cori system at NOSC, at Lawrence Berkeley National Lab, they added a file system with a global shared namespace that can take the data from memory to an SSD-based burst buffer, which is faster than the parallel file system that is based on the hardware disks, hard disks. And that reduces the gap, but it's not that significant if the SSDs are located outside the outside the compute node. So the new systems that are coming up are planning to add more levels of storage hierarchy, and also new types of storage class memory, like high bandwidth memory, Optane, and all those things are coming up. And in addition to the CPU memory, the location where the data has to be read or written to, moved from and to, are also adding up, like GPU memory or FPGAs. So not all the systems may have all the layers, but some of the systems have all the layers, and some of the systems only have a few layers. So, but most of the systems have this SSD-based node local storage. So the problem with this filling the gap is increasing the depth of storage hierarchy also increases the complexity in using them. The software is playing a role in trying to fill that gap more elegantly. So some of the software libraries that are playing a role in that aspect are these high-level I/O libraries such as HDF5, NetCDF, and PNetCDF, and I/O middleware that can either be accessed through the applications directly or through the high-level I/O libraries such as POSIX and MPIO. And they go deal with the file systems such as Lustre, GPFS, Data Warp, which is a burst buffer based on Cray. And I/O hardware itself is typically disk-based or SSD-based, but new types of storage class memory is also coming up. So the thing I'm focusing, or the project I'm leading, is to improve performance of HDF5. So what is HDF5? I would just give a very, very brief overview of HDF5. It is a hierarchical data format, version 5. It is an open file format designed for storing and retrieving high volume and complex data. It's an open source software, works with data in any format, and it is an extensible data model. There you can add structures for data organization and specification. It is, as I mentioned, it is designed for high-level, high volume and complex data. It works on every size and type of systems. You can work with HDF5 on cell phones to supercomputers, and it is designed for flexible and efficient storage and I/O. It hides the complexity of the system at the very high level API level. It also supports long-term data preservation with a very good file format specification. So this slide shows more details of that from HDF5. And it is currently, the software itself was released in 1998, and it is maintained by a nonprofit company called the HDF Group. And we collaborate with that with HDF group to add more features into it. And the HDF5 has the highest technology readiness level from NASA, and they use HDF5 for storing their significant amount of data. And it is heavily used on DOE supercomputing systems. If you take a look at this library usage on Cori and Edison in 2017, HDF5 parallel and HDF5 are among the top 5 most used libraries. And in the ECP, many ECP means Exascale computing project. So the HDF5 is critically required by several applications, and overall it is important and many ECP applications depend on HDF5. It has a very high coverage of ecosystem in terms of third-party libraries on how to use HDF5 library easily, and also various visualization tools that that can read the data from HDF5 much easily and visualize the data. So the overall ecosystem is very rich. So a HDF5 file is a container that holds objects. So any type of data can be just thrown into the file, and the HDF5 manages it. And the data model contains 6 abstractions: data set, group, and attribute. Data sets are the actual data you're storing, and then the group is to hierarchically combine these data sets, and attributes describe the data. And you can also have links and data types and data space to decorate the data itself, to add the self-describing nature of the data. If you look at the HDF5 data set, they organize and contain the data elements here. So HDF5 data type describes the individual data elements, and the data space describes the logical layout of how those data elements are organized. So as I was mentioning, groups and links connect organize the data sets and the attributes in a way that in a tree type of architecture, and then the links connect those things. And the core APIs are creating a file, creating a data space, and creating a data set, and do the I/O operations on the data set and close all of them in the same order. So that is very, very basic 6 or 7 APIs that are very heavily used, and you can start using HDF5 with these things. If you want more adding metadata, using various options to store and lay out the data, these are some other common routines that are used. And in the red text here, these are the ones that enable using MPI/IO, which is parallel IO, to set HDF5 to use MPI/IO internally. HDF5 downloads are available here. The latest release is 1.12.0, and the source code is available on GitHub now. So if anybody is interested in contributing to HDF5, this is the place to go through. And HDF5 also has several pre-built binaries provided by the HDF group. So all those information is here, and HDF5 supports compression of the data, and the library szip and zlib are built with, and they come in the pre-built binaries. Okay, so now shifting gears to the more advanced and more interesting part of what we are doing in this project. is HDF5, developing and delivering Exascale ready HDF5, how to make HDF5 ready for very large scale systems. So this is a summary of the features that we have been working on. A virtual object layer to open up the HDF5 API to new storage methods and architectures that are coming up. Asynchronous I/O to overlap I/O operations with computing operations and hide the I/O latency and improve the overall performance seen by the applications. Since there are multiple layers of storage in the hierarchy, using caching and prefetching to improve the performance and reducing the I/O gap is another approach we are developing. And the next one is subfiling. The current approach in HDF5 is storing all the data into a single large file. If there, we have worked with applications that develop more than 300 terabytes of data into a single large file. But there are various problems with moving the data around. So we have been introducing this subfiling approach where there will be a small number of HDF5 files, which the number can be defined by the user, but allows writing or reading multiple subfiles. Efficient, since GPUs are becoming workhorses of most of these upcoming systems, we also want to support moving data between GPU and storage. So we are working on that. So I will go into each of these features in next. So virtual object layer, it provides an application with the HDF5 data model and API, but allows different underlying storage mechanisms. So for example, there are two types of virtual object layers. Some are pass-through, which just intercepts the API and just goes through the native or some other terminal APIs. Terminal APIs are actually dealing with how the data is stored at the end. So there have been several virtual object layer connectors already available. Some of them we are developing, such as the asynchronous caching, data elevator, independent metadata. And the native is something that has been existing among the terminal layers, terminal virtual object layer connectors. And Deus is a new object-oriented file system or data management system from Intel. There are also others such as REST API and connecting the HDF5 API with the REST API to work with cloud computing environments. So the feature itself is now available in 1.12.0 and 1.12.1 that is coming up. More details are available in this paper if you're interested. So the asynchronous I/O is to overlap the I/O operations while the application is busy with computation. So this is in the synchronous approach where there are iterations of computations and I/O operations. So for example, compute and write here, and while the data is being written, compute stops in a synchronous fashion. And then the next compute starts after the write is done. And again, the write happens while the write is happening, the compute stops. But there is no need to wait for this write. So we can make this asynchronous overlapping of write with the next compute and save some time at the end. The last one in this, the last time step may have to wait until that is written to the data and making sure the data is available for next step. Okay, so there is a significant amount of technology description in this paper if you're interested, and there is also going to be a new paper coming up on this, which describes giving more control on when to do asynchronous and control on the asynchronous operations. The current performance, we see that if you are using HDF5, this is the performance we are seeing. And if we can overlap only 50% of the time, we save about 40% of the time, because the last time steps has to wait. And if we can overlap all of the IO time or read time or write time with the compute time, we pretty much see very small amount of IO time. So overall, what we are envisioning here is the IO time is not seen by the application that by a significant amount. So it is going to be very minimal, just one time step or slightly more than that for the overhead of maintaining the asynchronous infrastructure, but over on the application would not see any of that overhead. Okay, and the next one is the using the deep memory and storage hierarchy efficiently. So we are developing a cache wall connector to use the node local storage for storing the data, and then in the background asynchronously move the data from the node local storage to the final destination of that data. So this way, the bandwidth that the application sees is the fastest bandwidth that is available to store the data. So we can also use the main memory if there is memory available. So the only time the application sees is the copying from the application buffer to the caching layer, caching memory that is available to us. So the performance we have been seeing on two HPC systems, one on Summit at Oak Ridge National Laboratory. So when we use more than 128 nodes, the node local storage, or the collective node local storage bandwidth is much higher than the writing to the GPFS file system. So there we see significant performance benefit. This is we can read at 1,000 nodes, we can reach almost 2 terabytes per second performance. And on Theta, at Argonne National Laboratory, we see that performance improvement even at 16 nodes and 32 nodes, and we pretty much reach the peak bandwidth of the node local storage that are based on SSDs. So if anybody is interested in trying this cache wall, it is publicly available at this site. Similarly, the async wall is also available in this HPC IO wall async location, and it will be released with HDF5 in the next few months, and it'll be available as a package, and anybody can directly use it. Okay, as I mentioned about subfiling, instead of writing a very large single shared file that has various issues, for example, moving a very large 300 terabyte file is a problem, so you can just split it into multiple subfiles. And on the other side, if we are writing all the data into a single file, the file system locking also may become a contention. So to improve on that, we have been implementing a subfiling virtual file driver, which is a level below the virtual object layer level. So that has been showing, the initial implementations of this is showing a significant performance benefit for one of the benchmarks that we are using. So the bottom blue line here shows the performance with the released HDF5 version, and with subfiling, we see a significantly high bandwidth as we increase the number of processes. Okay. As I was mentioning, GPUs are pretty much becoming a part of almost all the large-scale supercomputing systems. So to support data movement from direct GPUs and then the storage, we have been seeing various technologies that are available in the GPU software. So one of the technologies that is coming on NVIDIA GPUs is NVIDIA GPU storage, GPU direct storage, or GDS, which allows avoiding the bounce buffer. Bounce buffer means current approach, or the slightly older approach, is copy the data, let's say in the write operation, copy the data from NVMe, the GPU to CPU, and then from there copy the data to NVMe. But that can be done directly from GPU to NVMe, or which is the storage device here. So if we developed an approach in HDF5 to wrap into the HDF5 API. So if you do HD5D write or D read, it directly uses this technology. So the improvement compared to the POSIX IO is significantly high, but we are also testing this with parallel IO and adding more adding a wall connector on top of cache wall, which I described earlier, and then improving the performance significantly for parallel applications as well. So there are some details in this paper, but more details will be coming up in a near future paper. Okay, so far I have been talking about HDF5. So one of the things that in HDF5 is it still follows the POSIX IO semantics, and the user is aware of where the file is located and how the data is stored on that file. But we have been thinking about, is it really needed for user to maintain all the files and how the data is laid out in those files? So we have been looking into, can we take the memory object in the that is stored in in the application space, and use that object abstraction as the first-class citizen for storing the data. So let's say the current status of storage systems and IO is, okay, there are new systems with various locations of storage, and the software, high-level libraries, IO middleware, forwarding layers, and others. And the applications use memory objects and then call the IO software to store the data. And to get the good performance, they have to tune the performance, tune the file systems, and all that information has to be known. There are various challenges in this. Multi-level hierarchy complicates the data movement, especially if the user has to be involved. And POSIX IO semantics hinder the scalability, because POSIX IO is more like old tracks, the system where you track playing music. So you do seeks and then read or write, and then go back and sync. So this is very slow, and if you are doing all this from thousands of processes, that becomes even slower. Extreme heterogeneity of various hardware, storage hardware, is also a major problem. So we went to various scientists in our lab and across the lab and asked, okay, what are the features that they would like? So some of the features that they were mentioning is they need easy interfaces and superior performance at the same time. And also autonomous data management, where they don't have to manage the data and how to move and where to store, which byte to go to, and all those things. And information has to be captured in a way that instead of just the dump bytes in the storage, also add some tags for information that can be easily managed and accessed. So towards that, we have come up with a next generation storage systems and IO to manage knowledge and also make things easier. So we provide the applications would be providing the memory objects and calling the high-level API, high-level storage APIs, and how the data is stored is more like a black box. Is it something feasible? Is what we have been trying. So transparent and asynchronous I/O and high-performant I/O, scalable, fault-tolerant, and autonomous. Yeah. So towards that, the proactive data containers is a system that we came up with. So the applications will be using the PDC or API, which is very simple, put get interface and array-based variable accesses. And this is something that these interfaces are something that have been used in cloud systems where you store the photos or music or something, you just put and get the entire thing back. But applying the same principles or interfaces to scientific data is what we are trying here. And the data placement in storage hierarchy and data movement in that is more transparent, automatic. So the users, there is no need to for the users to know where the data is stored, in the sense that when they want the data, they can access it, not where it is stored. And if they really want to see the data, there is a client level interface. They can extract it and convert it into different formats of data. And the towards capturing the information, we also add provide capabilities to store any types of rich metadata, and also connect results with the raw data and maintain relationships between different objects, so that information is well maintained. So to do that, we maintain various servers. One of the metadata server, data movement and optimization server, analysis task scheduler. So if a user wants to perform an analysis while the data is moving, they can register an analysis function to the system, and that function is executed in the system. So the currently we support writing data to or maintaining the data in PDC system and using the burst buffers and Lustre. And we also have some plans to develop the interfaces to DAOS connectors. The high-level API looks like create containers and add attributes to those containers, put object, get object, and delete object. And when the user application is working on their buffer or the memory object, they lock it. And when that lock is released, it is mapped to the PDC object, and the PDC object is moving the data when then there is no lock. So the array specificness, because it's not only just putting a petabyte of data and getting it. The scientific data also deals with adding accessing small amounts of data, so they can map that small amount of data and access or read or write those data. So the lock and release help that when to move the data. So I'm not going into the details of these in the system because of the time, but please go through these papers, and we have a website at this location. So there are a lot more number of papers, and we have also recently released the software. So if anybody is interested, this is a very good place to start using the system. Okay, so to conclude my talk, the Storage systems and I/O are moving towards providing the easy interfaces that are helpful for science and also obtain superior performance on large-scale systems. Simpler object interfaces are a typical way to go towards that. And data movement and data management should be more autonomous in the sense that the user doesn't have to maintain how everything is maintained in the file system. So that helps the scientists to focus more on their science than more on less on the data management and more on science. So to facilitate managing information, capture rich metadata, and enhance the search capabilities to exactly access the data that the users are looking for, and perform analysis and transformations of the data while the data is in moment. Okay, so if anybody would like to contact me, these are my coordinates, and contributions to this presentation are from various projects, and we thank Exascale Computing and Department of Energy in the USA. Right, thank you, and if you have any questions, please send them to me. Thank you.